Hey everybody. Today we're talking about Bayes' rule, also known as Bayes' theorem. At the heart of Bayesian statistics, which is a wonderful and complicated field, there's a very simple idea that the probability that an event will occur should be updated as new information comes in. Mathematically, that's encapsulated with this formula. The probability of B given A is equal to the probability of B times the probability of A given B divided by the probability of A. Obviously, since there's a p of a in the denominator on one of these sides of this equation, we have to assume that the probability of a is non-zero. Assuming that's the case, Bayes' theorem is really just a restatement of the multiplication rule, which says that the probability of a and b both occurring is equal to the probability of b given a times the probability of a, or, equivalently, the probability of a given b times the probability of b. If you take the rightmost equality there, and divide by probability of A, you get exactly the expression of Bayes' rule in that last slide. Bayes' theorem comes with new terminology. The probability of B is called the prior probability. It doesn't reflect any information at all about whether or not A has or has not occurred. Probability of B given A is called the posterior probability, and it does include information about whether or not A has occurred. Let's do an example. Suppose that a medical test for a certain illness has a false positive rate of 1%. So that means among people that don't have the illness will still get a positive result on this test 1% of the time. It also has a false negative rate of 9%. So that means that among people that do have the illness will get a negative result 9% of the time. If the overall prevalence of the illness is 12 per 100,000 people, find the probability that someone who tests positive for the illness actually has it. We're going to use the abbreviations plus and minus for the events that the test is positive and negative respectively, and capital Y and N for the events that the patient has and does not have the illness, again, respectively. Using that notation, we can take that word problem that we just had and write a bit more mathematically. P of Y equals 0.00012, P of plus given n is 0.01, and p of minus given y is 0.09. We're going to compute the probability of that the patient has the illness given that they have a positive test using Bayes' theorem, which in this context says p of y given plus is equal to p of y times p of plus given y over p of plus. Right now we know p of y, but not the other things on the right-hand side here. We know the probability of a positive result given that they don't have it, and the probability of a negative result given that they do have it. But the events negative given that they have it and positive given that they have it are complementary. And of course we know the probability of getting a negative result given that they do have it is 0.09. Therefore, the probability of a positive result given that they do have it is 0.91. Plugging into Bayes' rule, we see all we need to get now is the probability of a positive result. We compute the probability of testing positive using the law of total probability. Basically, breaking up the event that you test positive into two situations. You test positive when you do have it, and you test positive when you don't have it. Each of those two events can be the probabilities can be computed using the multiplication rule. The probability that you test positive and have the illness is equal to the probability of testing positive given that you have the illness times the probability of having the illness. Similarly, the probability of both testing positive and not having the illness is the probability of testing positive given that you don't have the illness times the probability that you don't have the illness. We can simplify a couple of those probabilities using the rule of complements. For instance, the probability of testing positive given that you have it is 1 minus the probability of testing negative given that you have it. Plugging in the probabilities that we know, simplifying a little bit, we get that the probability of a positive test result with no assumptions on whether or not you have it is 0.0101. Notice how close that probability is to the false positive rate of 1%. So the probability of testing positive and the probability of testing positive when you don't have the condition are pretty similar to one another. We're finally ready to compute the calculation that the person has the illness given that they've tested positive. Plugging in everything that we know and have figured out, we get it that it's about 0.0108. Before the test, the probability that the person had the illness was 0.00012, the prevalence rate of that illness. After the positive test, it went up to 0.0108, so obviously much higher. But even so, there's still almost a 99% chance that the person does not have the illness. Even though we applied the law of total probability as a separate step, it's often integrated into Bayes' rule directly. So basically take out the denominator on the right-hand side, the probability of a positive result, and replace it with a formulation that uses that law of total probability. This formulation is powerful because it only involves probabilities that are typically known to us. More generally, if you have a bunch of sets, B1 up to BR, which are disjoint and cover all of the sample space S, in other words, they form a partition of the sample space S, then Bayes' rule can be written like this. The probability of BK given A, so BK is any one particular B of interest, is equal to the probability of B sub K times the probability of A given B sub K times the sum of over all the i's, all the subsets B sub I, probability of BI times the probability of A given BI. The version of Bayes' rule from the last example was just the special case where the sample space was partitioned into just two sets, Y and N. You have the illness or you don't.